Hi everyone, Mr. Coxford here. In today's video, we're going to look at series circuits. So to start, we first have to know how to draw circuit diagrams. And we're going to look at the individual circuit elements and then figure out how to combine them all together into a circuit. So to start, we're going to look at a single cell. A cell is an electrical power supply. It is what provides the electrical potential energy to charges so that they can flow through a circuit. And it simply looks like this. It's a short line and a long line, and connected to it are the wires that lead to it and from it. The short line here represents the negative terminal of the battery, and the long line here represents the positive terminal of the battery. You don't have to draw those plus and minus signs, but if they're helpful for you to remember, you can draw them on there. What we remember is that current as in conventional current, the flow of positive charges will flow out of the positive terminal of this battery. That's the direction that current will flow. Now, a battery is simply a collection of cells. So you take a bunch of individual cells and stack them together, and you end up with a battery. And so what does that look like? Well, it simply looks like a bunch of cells, short terminal, long terminal, short terminal, long terminal. You just stack those all together. Here is 4 cells combined into a 4-cell battery, with again the positive terminal being the furthest to the right alongside, and the negative terminal of this battery being the short side. Simply, a battery is multiple cells. The next circuit element that we'll be using is a resistor or a load. This could be, again, a variety of things. It could be a light bulb, it could be a refrigerator, it could be a phone charger. We'll typically just draw these as a resistor, but it could represent any sort of load. So a resistor simply looks like this. It's sort of a jagged line in a circuit. And then a switch could look like one of two things, depending on whether you want to show it as open or closed. Typically, you'll show an open switch if you're even going to draw it, but here's your switch. You have these 2 little nodes there, and connected to it is sort of this arm that can open and closed. So here's our open switch. We can see it's not connected, and then if we were to draw a closed switch, we'd simply sort of flip that switch closed. Right, so here's closed. All right, so those are the basic circuit elements, and then connecting all those together will just be some wires, which are just simply lines. So let's take a look at an example of a circuit that we might want to draw. So we're going to connect 3 D cells. Imagine a D battery. We're going to connect 3 of those D batteries, or they're actually cells because they're just individual little units. So 3 D cells are placed in a battery pack to power a circuit containing 3 light bulbs in series. Let's draw a picture of the circuit, and then we'll draw a circuit diagram. So a picture of the circuit is sort of your physical representation. What would this actually look like if you were to draw it? And so it would, well, here, let me bring this up. It would look something like this, right? We have our 1 D cell battery, 2 D cell batteries, 3 D cell batteries connected to 1, 2, 3 light bulbs in series. So series means one after another. So we've connected these all in series, and we can see that it forms a complete loop. The positive terminal of the battery is connected to the negative terminal of the battery, so current can run. And here we have a complete circuit. So let's draw this as sort of our circuit drawing. We can have battery, and another battery, and another battery. And then connected to that are 3 light bulbs. My light bulbs are going to be amazing, thank you. There's 1 light bulb, right, with the little filament there. Okay, I'm going to just repeat that. Here's another light bulb there. And a 3rd light bulb there. You can see why I got into teaching physics and not art. Okay, so there's a little circuit diagram. Circuit picture. Now a circuit diagram, let's convert these into their appropriate symbols, which we can see up here. And we can see here is the circuit picture, circuit diagram, instead of drawing the light bulbs, there are circuit symbols for light bulbs. You can see them. There's actually a variety of ways to draw them. It could look like this, but often, as I said, we will, instead of drawing light bulbs or a refrigerator, we'll just draw them as resistors. So instead, here is an actual resistor. This is what a resistor looks like, but the symbol for a resistor, again, these squiggly here. And so we can see here is our circuit diagram. We have 3 cells stacked next to each other, and then 3 resistors. So let's draw that. And instead of drawing them spaced out like it was in that diagram, let's draw them squished together to show a battery. So here's 1 cell, 2 cells, 3 cells, and then we have 1 resistor, 2 resistors, and 3 resistors. Great. So now let's talk about series circuits and what we can understand about series circuits. So the word series means one after another. So if you have a series circuit, it means that elements in that circuit are connected one after another. Here is an example of a series circuit where all of the elements are connected one after another. Another way to talk about it is that each device or load or resistor is connected so that there's only one pathway for which charge can flow. Current only has one loop that it can flow through. And the charge will flow through each resistor or each load in a consecutive fashion. It will flow from the positive terminal of the battery through the first resistor, through the second resistor, through the third resistor, and then back into the battery, and it will continue going through that loop. Now, we need to understand something called equivalent resistance. Equivalent resistance is looking at all of the resistors that are connected to a battery in a series circuit and figuring out what is the total resistance, what is the equivalent resistance of all of those resistors combined. So here's an example. As far as a battery that is pumping charge is concerned, if we have 2 6-ohm resistors that are connected in series, that would be the same as 1 12-ohm resistor. So let's illustrate that. Here is a 6-ohm resistor and another 6-ohm resistor. There's 6 ohms and there's 6 ohms. This is the same as a single 12-ohm resistor. Now notice we don't draw the resistors bigger or smaller, just the label indicates how big or small that resistor is. Another quick example, imagine we have, let's say, an 8-ohm resistor and a 10-ohm resistor. Well, this is the same as, what do you think? It is the same as an 18-ohm resistor. We simply just add them together. And this can even go further if we have 3 resistors in series. Let's say we have a 2-ohm, a 4-ohm, and a 10-ohm. This is going to be the same as 2 plus 4 plus 10, 16-ohm resistor. These here, these are called equivalent resistances. So if you're asked, or if you're needing to find the equivalent resistance of some series circuit resistors, what we would do to find the equivalent resistance, Req, that's going to equal, well, if we're saying these are in series, right, this little s here, this means series. So to find the equivalent resistance for resistors in series, it's simply going to be the sum of all of the resistors added together, right? So however many resistors we have, 3 resistors, add them all together, 10 resistors, add them all together. If they're all in series, just add them all together. That will give you the equivalent resistance. So here, this is an important equation that we want to know. Okay. Now let's talk about current and voltage in a series circuit. What is going on with the current, the flow of electrons or the flow of the charges in the circuit, and what's going on with the voltage gains and voltage drops in a series circuit. So something that you may have seen in that lab is that the current is the same everywhere in a series circuit. It means that, well, let's actually take a look to remind ourselves. If we have a, let's show some current here. We can see the arrows here that are flowing are showing the flow of charges within the circuit. And you can see that no matter where we are in the circuit, up here, these arrows are flowing at a certain rate. Down here, they're flowing at a certain rate. They're flowing at the exact same rate everywhere in this circuit. And we can confirm that if we take an ammeter and we want to figure out, okay, what's the current up here? It's 0.9 amps. We move it over, it's 0.9 amps. We move it down here, it's 0.9 amps. Everywhere in this circuit, it's 0.9 amps. And if we were to increase maybe some of the resistance here, we notice you can even watch the little arrows. The arrows slow down as there's more resistance. It speeds up as there's less resistance. And that change happens everywhere in the circuit. 0.33 amps, 0.33 amps. So what we would say is that the current that is flowing out of the battery is equal to the current going through the first circuit element, the first resistor. It's equal to the current going through the second circuit element. It's equal to the current going through the third circuit element. It's equal to the current going through every single element in that circuit. The charge will flow at the exact same rate through every circuit element. And then we can use that and we can combine it with Ohm's law. Ohm's law, remember, gives us the relationship between voltage, current, and resistance. And so if we know that the current through the battery, we're calling that I battery, the voltage of the battery, maybe it's a 9-volt battery, divided by REQ. This is the total resistance experienced by the circuit or experienced by the battery. So if we have 3 resistors connected to the battery, a 2 ohm, a 4 ohm, and a 10 ohm resistor, combining those together to a 16 ohm resistance, that's the resistance that is experienced by the battery. So to figure out how much current is flowing out of that battery, take that voltage, the battery voltage, divided by the equivalent resistance of the circuit, and we will determine how much current is flowing out of that battery. And now in terms of voltage in a series circuit, the voltage supplied by the battery is equal to the sum of the voltage drops in each resistor. Let's take a look. So I'll get rid of this ammeter, and let's pull out this voltmeter. I'm going to reset this just back to 10 so that we have a nice even circuit. Each of these resistors is a 10 ohm resistor. And we have our 1, 2, 3 9-volt batteries. And here's what we're going to see. I'm going to switch this back to this diagram just so that we can visualize a bit more what's going on. So what I'm going to do, I'm going to show you here, these batteries have 27 volts. Means that the top of the battery has 27 volts more potential than the bottom of the battery. There's a 27 volt potential difference. And then what we can see is that as we move along the circuit, notice as I'm moving along this top wire, the voltage is not changing, the potential difference is not changing, but then when I get across this first resistor, we went from 27 volts down to 18 volts. There was a 9-volt drop across that first resistor. And then we move along, we stay at 18, stay at 18, stay at 18, and then we go across the second resistor, and now we're at 9 volts. There was another 9-volt drop across that second resistor. And then we continue, and we go across the third resistor, and now we're down to 0. We went from 9 to 0. There was another 9-volt drop. And notice now we are connected to the same wire as the black lead on this voltmeter, and there's no potential difference between these leads, which should make sense because there's no difference in energy when we're on the same wire. The other way we can see that is if we compare to the top terminal of the battery, okay, there's no voltage difference here. we're at 0 volts. But then when we go across the first resistor, we go down 9 volts, -9. And then we go across the second one, now we're down 18. And then we go across the third one, now we're down 27. Compared to the top of the battery, we're now 27 volts lower. We have 27 joules per coulomb less energy per charge, or per coulomb of charge. Okay, so let's put that into an equation here. It says that the voltage supplied by the battery is going to equal to the sum of the voltage drops in each resistor. So the voltage drop across resistor 1 plus the voltage drop across resistor 2 plus the voltage drop across resistor 3 plus whatever other voltage drops we have in a series circuit, add those all together. It's saying that all of the energy supplied by the battery is going to be used up by the time we get through that circuit. Okay, let's look at an example of this. So we have a simple series circuit here. We have a 9-volt battery, a 3 ohm resistor, a 4 ohm resistor, and a 2 ohm resistor in series with it. And we are going to find a few things: the total equivalent resistance, the current flowing in the circuit, or the current flowing out of the battery, the current flowing through one of the resistors, the voltage drop across each of the resistors, the total voltage drops. Let's see if we can use these things we've just learned to unpack this. So first I have constructed this circuit here, and we have our 9-volt battery, we have our 3 ohm resistor, we have a 4 ohm resistor, and a 2 ohm resistor. And let's first look at the current here. And we're going to see 1 amp of current flowing in this circuit. Let's see how we can get that. Okay. So first thing we need to do is to find the total equivalent resistance of the circuit. This is a series circuit, so the equivalent resistance for a series circuit is going to be the sum of all these circuit elements. It's going to be 3 ohms plus 4 ohms plus 2 ohms. The equivalent resistance of this circuit is 9 ohms. And then to find the current that is flowing through the circuit, it's going to be the current, that's the current flowing out of this battery. It's going to be the voltage of the battery divided by the equivalent resistance, the resistance experienced by the battery. So it's a 9-volt battery, it's a 9 ohm resistance. 9 divided by 9 is 1, and the unit for current is amps. So what this says is that we have 1 amp flowing out of the battery, but we also know that that means we have 1 amp flowing through resistor 1, and 1 amp flowing through resistor 2, and 1 amp flowing through resistor 3. We have 1 amp flowing everywhere in this circuit. So to figure out the current flowing through the 3 ohm resistor, well, we know that I1 is equal to I2 is equal to I3 is equal to the current through the battery. The current is the same everywhere, so it's 1 amp. Okay, now to find the voltage drop across the 3 ohm resistor. Well, let's use Ohm's law. Ohm's law tells us the relationship between current and resistance and voltage. The voltage drop across the 3 ohm resistor, that's this guy right here. So this is circuit element 1, R1. So V1 is going to be I1, R1. V is equal to IR. That's Ohm's law. So if we know the current through that element and the resistance of that element, multiply them together, we can get the voltage drop across it. So 1 amp flows through it. It's a 3 ohm resistor. So 1 amp times 3 ohms is 3 volts. There's a 3 volt drop across that first resistor. The voltage drop across the 4 ohm resistor, so that's the second circuit element, it's going to be I2, R2. Again, 1 amp flows through it. It's 4 ohms. So in this case, there's 4 volts dropped across it. more voltage dropped across that bigger resistor than the 3 ohm. And then for the third circuit element, the 2 ohm resistor, I3R3, it's going to be 1 amp times 2 ohms is equal to 2 volts. Smaller resistor, smaller voltage drop, less energy used to go through that circuit element. And then last question is, what is the total voltage drop across all of the resistors? So this is what it's saying. What's V1 plus V2 plus V3? It's 3 volts plus 4 volts plus 2 volts is 9 volts. And notice that that is the voltage that is supplied by the battery. This is equal to the voltage supplied by the battery, which we know for a series circuit should be the case. All of the voltage supplied by the battery needs to be used up by the time we complete that loop. And let's just double check that on our simulation here. Let's move that out of the way. Again, 1 amp, that's what we had calculated. So let's see. It's a 9-volt battery. Bingo. Okay, let's see. As we go through our, what is this? Our 3 ohm resistor, we go from 9 volts to 6 volts, a 3 volt drop. And then we go from 6 volts down to 2 volts. That's a 4 volt drop. And then we go from 2 volts down to 0 volts, a 2 volt drop. Perfect, just like we calculated. Okay, that's it for series circuits. In the next video, we'll look at parallel circuits. Take care.